And the coverage here will be chapter 46. Right, we took 3 examples on Wednesday. So today we will continue to offer, I think, 2 more examples. All right, so let's read the 2-dimensional. Vector space over C. Okay, so over the set of all complex numbers in letter T is the linear operator of V. Okay, and with that V, so let V be a basis for V. Okay, a basis for V. And then let A be the metric representation of G relative to basis V. So that would be say 1, 2, minus 1, minus 1, 4. So now determinant of A minus lambda I is equal to lambda square plus 1. So this is lambda I, lambda plus I. Okay. And so T is 2 eigenvalues. Lambda equal to I, and then lambda equal to minus I in the scalar field, because the scalar are all complex numbers. Okay, now, so we can see as before, so we can find an eigenvector. Okay, U. Okay, an eigenvector of A, associated with the eigenvalue lambda equal to I in the kernel of A minus lambda I 2 times 2. Right, so the number comes to I here. Right, so it's called U from here. Because it's an eigenvalue, so the kernel is non-trivial. Right, so we can find an eigenvector which is just a non-zero vector in this kernel. Alright, so we call it U. Also, we can find an eigenvector of A associated with eigenvalue lambda equal to lambda I in kernel of A plus I 2 by 2. Right? And this eigenvector we will call W. Now, with the new right? Okay. Alright, now the eigenvector U is taken from this kernel, and the eigenvector W is taken from this kernel. And we next show that the set consisting of U and W is linearly independent. And as follows. So let alpha U plus beta W is equal to the 0 column vectors, right, in C2. Okay. Then maybe I will do that later in a theory. Okay. So let me I think it's too early to say it now. Right. So I will. We will. As I said, we will show that. C one UW is a linearly independent set. Right? And then C is that's C. I'm sorry. That's C. So C is a basis for C2. So the set of all two-dimensional complex column vectors. All right. So now with C, we have TU equal to IU and TW equal to minus I W. Sorry. I think okay. Too quick. Let me see. Oh, okay. I vector and alpha 1, alpha 2, and okay, sorry. beta 1, beta 2, here. Okay. Right. Now, we let u equal to alpha 1 b1 plus alpha 2 b2, and w equal to beta 1 b1 plus beta 2 b2. The reason is that we want, this is just a b coordinate, so it's the b coordinate of vector u, and this is the b coordinate of a vector w. Yeah, right. And we will show that. We'll show that C equal to W. Linearly independent set. And then a basis so I have to be careful because with the metric representation A, what we find is just b coordinates. Okay. So we find a vector, eigenvector of A, right? And then we will reconstruct a vector in V such that its b coordinate is equal to alpha 1 or 2 equal to this column vector. And also we find a vector W in the vector space V such that its b coordinate is equal to beta 1, beta 2. Okay, and so you can check. Then we have. Then this one becomes to. Then so we know. All right. Then take U. Okay. So this is alpha 1 T U1 plus alpha 2 T U2. Okay. And then by taking the b coordinate, so we have alpha 1 b coordinate plus alpha 2 b coordinate. Okay? And this is b1 b coordinate. So this is A, and so this is I, alpha 1, alpha 2. Right? Because that alpha 1, alpha 2 is the eigenvector of A, also said with eigenvector. So we can go back to C. Right? We have this one because this is T, right? By our definition, right? We know the metric representation of T relative to basis B is this matrix. So that would be A. So this is A. All right, and so we go back. So we go back to so that the TU is equal to I alpha 1 V1 plus I alpha 2 V2. Because we reconstruct. We know the B coordinate. So the TU, right, can be reconstructed, okay, by using the B coordinate relative to the basis B. That, and this one is I alpha 1 V1 plus 2 V2. But alpha 1 V1 to be is just U. Okay, so we show so that I is eigenvalue of T, and U is an eigenvector of T associated with eigenvalue I. Alright, similarly, we know, we take a look at, and so this is P, beta 1, V1 plus beta 2, V2, so this is beta 1, P, V1 plus beta 2, P, V2. And now, we show that W is also an eigenvector of P, so we take the B coordinate. So this is becomes to, okay, so we take the B coordinate, and then express this linear combination of column vectors as a matrix multiplied with a column vector. Okay, and once again, that this is A, beta 1, beta 2. But beta 1, beta 2 is selected from here. And and this is the eigenvector of A, this matrix A associated with eigenvalue minus lambda. So this is minus lambda and the beta 1 and beta 2. Okay. So the B coordinate of TW is equal to this one. So we can reconstruct TW by using its B coordinate. So its B coordinate will be minus I beta 1 come to V1 plus minus I beta 2. Okay, so this is the construction. And minus I beta 1 V1 plus beta 2 V2. So it's minus I and the W. So we put that TW is equal to minus I W. So minus I is an eigenvalue of T, and W is an eigenvector of T associated with eigenvalue minus I. All right, and so with this one, so that the matrix representation relative to C, which is T, U, C, T, W, C. Okay. So this is become to TUC. TU is here. TU is IU plus 0W. Okay. All right. So the C coordinate of TU is I and the 0. What is that? This is 0 U plus minus I W. Right. So the C coordinate of TW is 1. It's 0 and minus 1. So it becomes to a diagonal matrix. Right. So the matrix representation of this linear transformation T, right, becomes to a diagonal matrix. So it's again diagonalizable. Right? Again diagonalizable. Okay, because we are talking about the scalar field is a complex number field. Unlike the third example we examined the last time, because in that time even we are considering real scalar field, and we don't have real eigenvalues at all. But when we consider them as the V as vector space over the complex number field, then we can diagonalize that. All right, and the fifth example is that this time A. Consider a linear transformation. So T V to V over linear over C. Okay. So again, V is a vector space over the complex scalar field, and T is a linear operator on V. And B is a basis such that okay, and B is a basis for B such that the matrix representation of this linear operator represent B is this matrix. Right, it's this matrix, and so we look at the determinant of A minus lambda I here. So we find this determinant of I minus lambda 1, 0, I minus lambda here, and so that this is lambda minus I square. All right, so the lambda is equal to I. All right, it's an eigenvalue. All right, so it's an eigenvalue of A. All right, with algebraic multiplicity 2. Alright, so with multiplicity 2. Okay? And so the kernel of so we want to find eigenvector, right? One eigenvector for because we have only one eigenvalue. So to find a basis like this one, we have to find two linearly independent eigenvectors, right? To form a basis. All right. So we look at minus I. So the kernel of I minus I, I is 0, 0, 0, 1. Okay. And what is that? This is the set of all alpha, 0, C. Okay. And so the dimension of the dimension of the kernel is equal to 1, and so it's less than 2. So we cannot find two linearly independent eigenvectors from this kernel. We can't find it. Okay, because its dimension is only 1. Okay, so by theorem in chapter 5 we studied it's impossible to find two linearly independent vectors in this kernel. Impossible. And so this one, this one is defined to be later on will be geometric multiplicity. Eigenvalue I. So the geometrical multiplicity of eigenvalue I, alright, is smaller than its algebraic multiplicity. That is the problem, and we will take care about that later on. Okay, so here, so that we cannot find a basis C U W. We cannot find a basis W for V such that you cannot find. You cannot such that you W eigenvectors for eigenvector associated with eigenvalue I. Okay, we can't. Okay, so we can't. So T has no diagonal matrix representation. Okay, no. So not only in real case, but also in the complex case, we may encounter the situation that the linear transition operator T has no diagonal matrix representation. Again, so to have a diagonal representation, right? This problem, but it's the common problem for any field, either real number fields or complete number field. Okay, so we will solve them some mechanics. Okay, so now we will proceed. So this is examples we know about when we are able to solve the eigen equations. Okay, so before that, I would like to introduce permutation. A permutation sigma on the set of all positive real numbers up to n is just a one-to-one function from, okay, and this set will be defined to be 1 to n. Okay, we use this interval, bracket 1 to n, from 1 to n to 1 to n. Okay. Alright, so a permutation is just a function from 1 to n to 1 to n, and it's one to one. Of course, it's onto because this is a finite set. So, example for n equal to 5, usually we express one-to-one mapping 1, 2, 3, 4, 5 by using an array like this one. So it's 2, 3, 5, 1, 4. Right? So that means that the sigma 1 is equal to 2, sigma 2 is equal to 3, sigma 3 is equal to 5, sigma 4 is equal to 1, and the sigma 5 is equal to 4. Okay. So this 1 maps to 2, 2 maps to 3, 3 maps to 5, 4 maps to 1, and 5 maps to 4. Okay. So this is the sigma will be represented by such notations. It's quite convenient. Okay, and we will let person be the state of all permutations 1 to n. Okay, and we will know that the size of this set, is n factorial. Why? Look at here. Any permutation can be represented in this way, right? So to put a number here under 1, right? You have how many choices? 5 choices, right? You can put 1 or 2 or 3 or 4 or 5 here. So you have 5 choices. Once you put 2 here, you cannot. Then you want to select. You want to select 1, right? But 2 has been used, so you have only 4 choices, right? Because you cannot use 2 again. So what you can put here is 1 and 3 and 4 and 5. You have only 4 choices. Right? So now you decide to put 3 here. Now and here, you have only 3 choices left. That is 1 and 4 and 5. And you select 5 here. That's good. And then here, you have only 2 choices, 1 and 4. Alright, and then select 1 here. And then no other choice, only 4 left. So this is only 1 choice. Alright, so the possible choices will be 5, 4, 3, 2, 1. So this is 5 factorial. So in general, the number of possible permutations 1 to n on this set will be n factorial. Okay, so this is the type. Right. Okay, and now for n to 5, we consider the elementary sigma 1. So we have okay, and so you can compare the identity matrix. So this is E1, E2, up to E5. One zero 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 1 0 0 0 up to 0 0 0 0 1. Okay. So this is identity matrix. So identity matrix consists of the 5 standard univector, uniro vector here. So E1 is 1 0 0 0, E2 is 0 1, etc. But E, if you permute the rows by using sigma, right? So in this one, this would be, if we use that one, E1 is 2, and E2 is 3, and E4, E3 is 5, and equals 1, and E5 is 4. Alright, so this matrix is what? It's 0 1 0 0 0. 0 0 0 1 0 0 0 0 0 1 1 0 0 0 0 and 0 0 0 1 0. Okay. Alright, so E is just obtained by permuting by row exchanges. Okay, so which shows that E is obtained by a series of row exchanges. Okay, so okay, so to find the determinant of E, okay, to find the determinant of E, so you have determinant of E2, E3, E5, E1, E4, right? You first of all, you exchange them 1 and 2. Okay, so you have -1 determinant of E1 here, E3, E5, E2, E4. Okay. And then you exchange these two rows, you get minus squared determinants of E1, E2, E5, E3, and E4. Okay, and then you do it again. So this time you exchange the third and the fourth row. So you get E1, E2, E3, E5, E4. Okay. And the last one you exchange the fourth and fifth row, and you get determinant of E1, E2, E3, E4, E5. Alright, so you go back to the identity matrix. And the determinant is 1. So you can see that if you exchange the rows arbitrarily, okay, from the identity matrix, you exchange them though. The determinant of this matrix will be either -1 or 1. Right? Because you can do row exchange again. So by several row exchanges, you will be able to find the determinant of B. Okay? And so it's either -1 or +1. So we define the sign of a permutation. Alright? So define the sign of a permutation could be the determinant of E sigma 1, E sigma 2, E sigma n. Means that we define the sign of a permutation to be the determinant of the matrix E, which is obtained by doing the row operations, the row permutations by using sigma. Okay? So that from E1 we go to E sigma 1, to E2 goes to E sigma 2. So actually, it's just a permutation of these n rows. Okay? So this is the definition. Which is either plus 1 or minus 1. So it's all sum. Okay. Any questions? So we define the sign this way. Okay. Okay, so now we come up with a lemma about determinant. (6.1.8) is called extension formula for determinant. Alright, so let A be Aij be an n times n matrix. Then the determinant of A is the summation of all possible permutations over first of all we have a sign of the sigma, and we have A1 sigma 1, A2 sigma 2 up to A and sigma n. So this is expansion. Okay, so let me see the proof. Alright, we call chapter 4 since the determinant function is linear. Okay, it's linear at each row of A we have, okay, the determinant right, so that this is their rows, and we express the first row as a linear combination of the standard row vectors, standard unit row vectors. So we have A, 1, 1, E1 plus A, 1, 2, E2 plus 1, 1, En, and R2 up to Rn. Okay? And the linearity of the determinant function at the first row, so this becomes to summation of, right, maybe I withdraw. A11, determinant of B1, R2, what's it, Rn, plus A12, determinant of E2, R2 up to Rn, plus plus A1n, determinant of En, R2 up to Rn. Okay, so this is the we have that. Okay, and we will write I1 equal to 1 to n, A1, I1. Okay, determinant of E, I1, R2 up to Rn. So we use this notation to express the linear combinations like that. Okay, and so I1 equal to 1 to n, A1, I1. And this time, I1, we will expand the second row. So the second row will be, here will be summation I2 from 1 to n, A2, I2, B, I2. Okay? So R2 is the linear combination of, with their component, the entries is A and J here. So that the second row, the entry of the second row, and so expressed as linear combination of the standard unit row vectors. Okay, and so by extension, A1, I1, A2, I2, and the determinant of E, I1, E, I2, and here. Okay, so we can continue to do so, right? Continue to do so. So finally, we will have I1 from 1 to n. Okay. Sorry, I forgot. I2 from 1 to n. A1, I1. A2, I2. Sorry. I forgot another sum. And the summation I2 from 1 to n, up to In equal to 1 to n, and A1, I1, A2, I2, A, n, In, and the determinant of E, I1, E, I2, E, In, there. So I1 can be from 1 to n, I2 can be from 1 to n, etc. In can be 1 to n. But if any two indexes are equal, then the determinant will be 0, because equal rows has 0 determinants. Right? Equal rows. For example, if I1 equal to I2, then the determinant is 0. So there are a lot of zeros here. The terms, they are here. They are, how many terms we have? There are n to nth power terms. Okay? Because here, you can select any entries of the first row. So you have n choices. And here you have can select any entry in the second row. So you have n choices, etc. So the number of terms is n to the nth power, a very big number. Okay, a very big number. But many of them is 0. Why? Because that if any index, for example, I1 equal to I2, then the term is 0. Or for example, I sub n equal to I sub 2, then the second row and the nth row are equal, and then the term is 0. Okay, so the only thing left is that if the index are all different, I1, I2, In are all different. Okay? And so that now that determinant of EI1, EI2 with the EIN not equal to 0, you can only I1, I2 up to In are distinct. Okay? Now, in this case, if they are distinct, we define a permutation. Sigma in Sn, right? Sigma 1 equal to I1, sigma 2 equal to I2, etc. up to sigma n equal to In. Okay? So, because I1, I2 up to In are distinct, just like so, i.e. the sigma is okay. So the index, the I1, I2, I3 is here, and because they are distinct, so they form a permutation, of course, right? So the making, the correspondence give us a sigma here. So sigma 1 is I1, sigma 2 is I2, etc. Sigma n is In. So a sequence of distinct integers from 1 to n, right? We find a unique permutation. Conversely, any permutation gives you a sequence of I1, I2 up to In of distinct integers from 1 to n. So they are 1 to 1. They are 1 to 1. Okay, and so in this situation, the determinant, so that the determinant of A becomes we can use the sigma, the permutation, right? And then A1 sigma 1, A2 sigma 2 up to An sigma n. Okay, and here we have determinant of E sigma 1, E sigma 2 up to E sigma n. Okay, so so how many terms do we have? We have n factorial terms. So we reduce. Originally we have n to n terms. Now we have n factorial terms only. But by our definition, this is the sign of sigma. Okay, so finally, sigma. the sign of sigma, because the determinant is either 1 or minus 1. And A1 sigma 1, A2 sigma 2, An sigma. Okay, and I will now prove the lemma here. Okay, so prove the lemma. Okay, so let's take a short break, just for 3 minutes. Okay. Alright, so now we will prove a major theorem. We prove 1.8. Let's see. B, a linear operator. On an n-dimensional vector space V, okay, over F, then determinant of P minus lambda I is a polynomial of degree and in the indeterminate lambda. Alright, so the determinants here, as we see in our previous examples, you can see that this determinant is actually a polynomial, okay? And degree is n. If the dimension of the vector space V is n, and within the determinant lambda, so it's a polynomial function. Okay, so now relate A to B is the metric representation okay, of P relative to a basis B or V. Right? So we can select an arbitrary basis B for the vector space V, and then use the metric representation of P relative to B, and it is A. Right? Because to compute the determinants, we use an arbitrary metric representation. Okay. All right. So then the determinant of P minus lambda identity is equal to the determinant of A minus lambda identity n times n. Alright, so that we have determinant of A11 lambda minus lambda and the A12, that is the A1n, A21, and here is A22 minus lambda, that is the A2n, that is the A1, A2, that is the A and n minus lambda. Here. So this matrix comes like that. And we will name this matrix as B matrix. So B11, B12, B1n, B21, B22, B2n, Bn1, Bn2, Bnn. Alright, where Bij is defined to be Aij. So Bij is equal to Aij if I not equal to j. So if the entries is off diagonal, then Bij will be the same as Aij. But if if I equal to j, then bij becomes 2aii minus lambda. So it's a linear factor of lambda. It's a linear polynomial, okay? So the entries here, these are linear. They are linear polynomials. But of the diagonal, the entry is just constant, aij. And this is a polynomial of degree 1. Okay? A polynomial of degree 1. Now, by our expansion formula, so this is summation over all permutation, the sign of sigma B1 sigma 1, B2 sigma 2, Bn sigma. Alright? Now, there is only one term with sigma I equal to I, means that we have an identity permutation for all such that sine sigma B11, B22 up to Bnn is equal to the sine sigma, because the sigma is identity, so the corresponding matrix has determined 1. Okay? So this is equal to A11 minus lambda, A22 minus lambda, Ann minus lambda. Alright? Alright, and this is a polynomial. Of degree n in lambda with leading coefficient equal to minus 1's nth power. Okay? So the leading coefficient is nth power of minus 1. Alright, so we have only one such term. And this term is, each term is formed by, for example, B1 sigma 1 is that from the first row, you select one entry. From the second row, you select one entry. And for the nth row, you select one entry from the nth row. But the entries cannot be in the same column. Okay? Right? Because the sigma 1, sigma 2 up to sigma should be distinct. So that the column index should be different. Okay? And this term has you have the greatest number with linear factors. Okay? Because once Bij is not, if I is not equal to j, then it is a constant. It's a constant. So so that all other terms are polynomials of degree less than or equal to n minus 1. Okay? Since that since Bi sigma I is a constant whenever sigma I is not equal to I. Okay? So if the selected entry is not on this diagonal, So that so you will have constant, and so the factors, because each term is product of many factors, right? And this factor can be a constant. A constant means that a polynomial degree less than or equal to 0, okay? Or it's a factor of degree 1, okay? They are product of polynomials. So only this term, because that sigma equal to I, so we have n linear factors. And with n linear factors, this term is a polynomial of degree n, and the leading coefficient is minus n power of minus 1, because here minus 1 minus 1. But all other terms are polynomials of degree less than or equal to n minus 1. Okay, so we conclude that the determinant of t minus lambda I is a polynomial of degree n, right, lambda with leading coefficient equal to minus 1 times power of minus 1. Okay, so we conclude, we finish the proof. Now, this polynomial, alright? So this polynomial determinant of t minus lambda I, this polynomial of degree, and right, is called a degree n in lambda, is called the characteristic. Alright, the characteristic polynomial of t. Okay, and we call determinant of t minus lambda I equal to 0 to be the characteristic equation. Okay? So thus, eigenvalues, right, of t are just the solutions of characteristic equation. Of the characteristic equation of t. Okay? So up to now you can go back to see our 5 examples, right? So every time we find a polynomial, actually every time we just find the characteristic polynomial. Right? And from the characteristic polynomial we solve the characteristic equation to find the eigenvalues. Okay? Find eigenvalues. Right? So now let alpha be an eigenvalue of t by solving the characteristic equation. That's what we find, an eigenvalue. Of course, it's possible that you can't find any eigenvalue. For example, in particular, if the scale are real numbers, and the characteristic equation, even though the coefficients are all real, but it may not have any real root, no real solutions. Okay, so in that situation, there are no real eigenvalues. We don't have any eigenvalues. Okay. Anyway, but suppose we have an eigenvalue alpha. So if lambda minus alpha, the x power, is a factor of the characteristic polynomial, but if we raise n plus 1, but we raise the power one more, it's not a factor of the characteristic polynomial, then M is called the algebraic multiplicity of the eigenvalue alpha of t. Okay? So for each eigenvalue, we can find its algebraic multiplicity. Alright, so for example, if we have a matrix representation like this is A, then the characteristic polynomial determinant of A minus lambda I becomes to, this is determinant of A minus lambda I 3 by 3, and which is minus 2 square and the lambda 1 times 1. Okay, so this characteristic polynomial can be factorized this way. So that the multiplicity, the algebraic multiplicity of eigenvalue 2 is 2. But the algebraic multiplicity of eigenvalue 1 is 1. Maybe you will see funny, right? So maybe I change my mind. 3 here. Okay. Maybe you say, oh, 2 to 2, 1 to 1, but just accident, right? So I just said, okay, if I change this entry by 3, then the characteristic polynomial will be like that. So we have eigenvalue 2 and eigenvalue 3. And the multiplicity of eigenvalue 2 is 2. The multiplicity of eigenvalue 3 is 1. For this example. Okay, so we define the algebraic multiplicity. Now we are going to define the geometric multiplicity of an eigenvalue. Now, for an eigenvalue alpha of t, we define the E alpha to be the set of all vectors satisfying the eigen equation with the eigenvalue alpha. So this is eigen equation, but we are given the specific eigenvalue alpha here. Okay? Right? So it consists of all solutions, all vectors in the vector space B satisfying the eigen equation. And this is actually exactly, so this the solution set of the eigen equation. P V equals to lambda V with lambda equal to alpha. Okay, specifically. And this is actually the kernel of T minus alpha I. Okay. Just kernel. So of course it's so from here it's just a kernel. Right? So we have a lemma, very simple lemma, 6.1b. Given an eigenvalue of a linear operator E from an n-dimensional vector space V E alpha is a subspace of V. Of course, because the kernel, we know kernel is a subspace of V already. Okay, so we already proved that before. Okay, so I'm not going to do it again. Alright, now this subspace E alpha will be called the eigenspace of T associated with eigenvalue alpha. Okay, so this subspace will be called the eigenspace. Sorry, eigenspace of T. Okay. Now, the dimension of the alpha is called the geometric multiplicity of eigenvalue alpha of T. Of course, the dimension of the eigenspace should be greater than 1 because the kernel is non-trivial. This is the definition for alpha to be eigenvalue. Okay. So intrinsically, geometric multiplicity always greater than or equal to 1. Okay. Okay, before we proceed to more results, I want to prove a lemma about a determinant. So determinant formula for Block triangular matrices. Okay. So the formula is that determinant of a big matrix A, D, 0, C. Okay. Suppose we have a block diagonal matrix, right? This is all 0 block. And the dimension, let's say A is n times n, and the C is m times m. So D is n times m, and here is m times n, right? So suppose we have a big matrix, okay? And by partition, we find that this corner is just a zero submatrix. Okay? Just a zero submatrix. Right? Then this determinant is equal to the determinant of A times the determinant of C. Okay? So this is n times n. This is n times n. So we have such a very nice formula. Okay? Nice formula, yeah. Alright, so for example, before we keep a proof, determinants 1, 2, minus 1, 1, 5, 7, 0, 0, 0, 0. Suppose we have a 4 by 4 matrix like that, and we find that this corner is a zero sum matrix. Then by this lemma, we know this is 1, 2, minus 1, 1 times determinants of 2 minus 1, 3, 1. Alright, and so it comes to easy 5.3, so it's 15. Like that. Okay, so we prove that if C is non-invertible, right? So if C is non-invertible, then A, B, 0, C is also non-invertible. So that determinant A, B, 0, C, because it's non-invertible, so the determinant is 0, and this is determinant of A, determinant of times 0, and this is determinant of A, and the determinant of C. Okay, so we have done. Okay, so if C is non-invertible, of course, determinant of C is 0, right? And then this is why? Why? Because look at here. C is non-invertible, means that the row of C are linearly dependent. Okay? Because we have m rows, right? We have m rows. So the m rows of C are linearly dependent. Now, even you look at the bigger rows, because we add zeros here. So these m rows are also linearly dependent. If we have rows, they are linearly dependent, then the m plus m rows are also linearly dependent. Because if your small set is already linearly dependent, you will add more vector into that set, still linearly dependent. Okay? So that this is non-invertible. Okay? Non-invertible. So that is easy to see. Okay? So this says that the m rows of C are linearly dependent. Right? so that the M rows of your C. Okay, so we turn the submatrix C into its reduced row echelon form, and which is an identity matrix and class N, because C is invertible. So when C is invertible, its reduced row echelon form will be the identity matrix. And then you see that the determinant of A, B, or C becomes to the alpha 1, alpha k, and the determinant of A, B, C, and concept. Okay? And the determinant of C is also alpha 1, alpha 2, up to alpha k, the determinants of identity. Because we do the same thing. We apply the same elementary law operations. Because every time when we apply law operation, we will, for example, maybe by scaling, maybe by row exchange, maybe by replacement. If by replacement, then the constant will be 1. We will not change the determinant. But if we do the row exchange, then we will multiply with -1. If we do the scaling, then we have to multiply with the scalar. Right? So that starting from this, we operate on the row on C is the same as on this submatrix, because here is always zeros. So we will end up with the same sequence of scalars here. And determinants here, determinants there. And we know the determinant of identity matrix is 1. Okay? So we're done. Okay? So now, alright, and so that the determinant of AD of C becomes the determinant of C and the determinant of A, D, 0 identity. Okay, so immediately this sequence of constants will be replaced by determinant C. Okay, so now we have determinant C already here. Now we will deal with this determinant. Alright, so we will use what? We will use the backward substitution, right? To cancel the D. Right? You see, backward substitution. Because we have 1, so that cancel, right? So that we have determinant of C and determinants of A and the 0, 0, I. Okay? By replacement. Okay? By replacement. Only. If we do the replace only, then we will not change the determinants at all, right? So because we can do backward substitution. So backward elimination. So we will do backward elimination. Elimination by replacement. Okay, so we'll do that. And then we will make the D to 0, but A will be intact. Why? Because here we have 0 here. So we do nothing with A. Right? So now this one becomes this one. Now, if A is non-invertible, okay? Now, if A is non-invertible, then A 0, 0 identity M times M is also non-invertible. The same reason why? Because if A is non-invertible, so the n rows of A are linearly dependent. Right? The n rows of A are linearly dependent. And then when you consider this submatrix, the n rows of this submatrix are linearly dependent. Okay? And so the n plus m rows in this matrix are linearly dependent, and so that it's non-invertible, of course. The same reason as that. Okay. Because we turn this branch to be 0, right? So, okay. So that determinants of A0, 0 identity is 0 equal to determinants of A. And then determinants of AE 0C is equal to determinant of C, determinants of A 0, 0 identity is equal to determinant of C and then 0, and the also determinant of C and determinant of A. And we have that. Okay? So we get the result. So the only thing left is that assume that A is invertible. Alright, so now we will apply, finally, applying elementary row operations. On the submatrix A and A0 matrices simultaneously. So we have determinants of A 0 0 identity M times M equal to beta 1, beta 2, beta R, and determinant of identity n by n, 0 0 identity m by m, and the determinant of A is the same as beta 1, beta 2, beta R, determinants of okay, so it's obvious that this product of scalars is equal to the determinant of A. Okay, so that So now, determinant of A 0, 0, identity M times M equal to determinant of A. Okay? So prove that because this is equal to 1, this is also equal to 1. Because this is the identity matrix. This is also identity matrix, so they are the same. And then, finally, determinant of A, B, 0, C, determinant of C, determinant of A, 0, 0 identity, equal to determinant of C and determinant of A. And then we have that. Finish the proof. We already consider all cases. And in each case, for each of those cases, we have the determinants of A, B, 0, C equal to the product of determinant A and determinant C. Okay, so we can use that. Okay, so now we are able to prove a major theorem again. Point 1.2, right? The geometric multiplicity of an eigenvalue alpha of a linear operator B on an n-dimensional vector space V over a scale field is no greater than the algebraic multiplicity of that eigenvalue alpha. Right. So geometrical multiplicity always less than or equal to the algebraic multiplicity. Right. So the proof is here. Okay, so let P be the dimension. So let P be the dimension of the eigenspace of P associated with eigenvalue alpha. Right? And we select a basis. The basis V1, V2 up to Vp, and order the basis for the eigenspace E alpha. Right, so P is the dimension. We know P will be greater than or equal to 1. And V1, V2 up to Vp, an order basis for this eigenspace E alpha. Now we extend the linearly independent set V1, V2 up to Vp to and order the basis B, which is V1, V2 up to Vp, and from Vp plus 1 up to Vn. For what? For V. Okay? This is true, right? A theorem in chapter 5 tells us that we can always extend from a linearly independent set to a basis, right? For the V, for the vector space. Okay? For the vector space there. Now, since TV1, because V1 is the basis for E alpha, so that it is alpha V1 because it's an eigenvector. It's an eigenvector, so it satisfies this one. All right, and so this is alpha V1 plus 0 V2 plus plus 0 Vp plus 0 Vp plus 1 plus a very long because we want to Vn. Alright? So TV1 is here. Okay. We want to find the metric representation of T relative to this basis B. Okay. So, but we have not. And TV2, this is alpha V2. Again, alpha V2. Because V2 is also in the eigenspace E alpha. So it satisfies the eigen equation. And this is 0 V1 plus alpha V2 plus 0 Vp plus 0 Vp plus 1 plus 0 Vn. Up to T Vp. Vp is alpha Vp. So it's 0 V1 plus 0 V2 plus alpha Vp plus 0 Vp plus 1 plus 0 Vn. Okay. But from Vp plus 1, right? Then we will have anything, right? So that would be say we will have say A P plus 1 1 P1 plus we have A P plus 1 1 1 plus A P plus 1 2 P2 plus A P plus 1 and Vn. Because Vp plus 1 is arbitrary, right? It is not an eigenvector associated with eigenvalue alpha. So that it can be anything. Because it's a vector in V. So by the base expansion, you have that. Okay, and so you finally Vn. This is A and 1, V1 plus A and 2. V2 plus A and N, Vn. Okay. So now that's the matrix representation. The matrix representation of T relative to the basis B is the now T3. So what is that? It's the TV1 B, TV2 B, so that TV3 B. Okay, and TV3 plus 1 B. So that TVN B. That's a big matrix. And so, what is that? Interesting thing. We have alpha 0, 0, 0, alpha 0, 0, 0, alpha. Okay? So we have diagonal entries, matrix, and the diagonal entries are all alphas. And we have D here. The column, the first column is alpha 0, 0, 0, and the 0, 0, 0, 0, and 0, 0. Okay? Because this column vector, right? Alpha 0, 0, 0, 0, alpha 0, 0, 0, and up to here 0, 0, alpha and 0, 0, 0. Okay? And then we have D and C, because this is arbitrary. The last are arbitraries. Okay? So we are arbitrary. And now we have a block diagram matrices. Okay? Right? So, so here this is P. This is M minus P. Okay? And so this is M minus P times M minus P. Okay? This is P times M minus P. Right? So the characteristic polynomial polynomial of P is f of lambda, determinant of P minus lambda, identity M lambda. Okay. And it's very interesting. This is determinant of alpha identity P times P minus lambda identity P times P. And we have P here, and 0 and C minus lambda identity N times P times N times P. Okay? Again, it's product diagram. So the determinants by our formula for block diagonal matrices, we find that this is equal to determinants of alpha minus lambda identity P times P. Alright, so this one determinants of C minus lambda identity. Okay? And what is that? The determinant is alpha minus lambda to the fifth power. Okay? And we have determinants of with G lambda. Okay? We have G lambda. So this G lambda is the characteristic polynomial of C. Alright, so it's characteristic polynomial of C. And but the factor here is that we have this part of alpha minus lambda. Okay, so we prove that lambda minus alpha this power is a divisor of the characteristic polynomial of P. Okay? So this implies that the algebraic multiplicity of alpha is greater than P, because that possibly the G lambda has a factor lambda minus alpha, possibly, right? But at least we have a P, right? So that the algebraic multiplicity of alpha is at least P. But this P is equal to the multiplicity of alpha. And then we have that. So we prove that for any eigenvalue alpha, its algebraic matrix is always greater than or equal to its geometric matrix. And this is the end of the proof. Okay? Any questions? Any questions? Okay, so we are able to prove that theorem. Because the theorem has been stated in the textbook without any proof. Okay. So I give you a theme of the proof for that, okay? By using such a lemma. Okay, and so now we need another important theorem related to a linear operator on an n-dimensional vector space V. Alright, if U1, U2 up to UK are eigenvectors of T corresponding to distinct eigenvalues number 1, number 2 up to number k respectively, then U1, U2 up to UK is a linearly independent set. Alright, so if we have k distinct eigenvalues, and for each eigenvalue we pick up and associate eigenvectors and put them together, then this set is linearly independent. Alright. Alright, so we do it, we prove it by contradiction. So suppose that U1, U2 up to UK, right, is linearly dependent. Right, suppose it. Right, so we let Uj plus 1 be the first Ui I from 1 to k such that Uj plus 1 is a linear combination of U1, U2 up to Uj. Okay? So that is because you must have a linear relation on this set. So you will have some Uj plus 1 such that it's the linear combination of the previous U. Okay? And we select J plus 1 as the first one. Alright, the first one such that it's a linear combination of that. Okay? Alright, so this says that U1, U2 up to Uj is a linearly independent set. Independent set. Right? It's a linear independent. But if we join Uj plus 1 into it, it becomes linearly dependent. Alright, so we select such a J there. Alright, so it's a linear independent set, and the Uj plus 1 is equal to alpha 1, U1 plus alpha 2, U2 plus plus alpha J, Uj. For some scalars, alpha 1, alpha 2 up to alpha J, not all zeros. Okay. All right. So now we apply T on both sides. So by applying T on both sides, right? Because we have, right? So we have T Uj plus 1 equal to alpha 1 T U1 plus alpha 2 T U2 plus etc. Alpha J T Uj. Okay, so when we apply them like that, okay, so now we have lambda J plus 1 and the Uj plus 1 because they are eigenvectors. So T Uj plus 1 is equal to lambda J plus 1 times Uj plus 1. And the alpha 1, lambda 1, U1 plus alpha 2, lambda 2, U2 plus alpha J, lambda J, Uj. Okay, so we have that. Okay, so this is one. But if we multiply the same equation, by lambda J plus 1, so we have Uj plus 1, alpha 1, lambda J plus 1, U1 plus alpha 2, lambda J plus 1, U2 plus alpha J, lambda J plus 1, Uj. And we do the subtraction. So this is 0 vector. And we have alpha 1, lambda 1 minus lambda J plus 1, U1 plus alpha 2, lambda 2 minus lambda J plus 1, U2 plus alpha J, lambda J minus lambda J plus 1, Uj. Okay? Which is a non-trivial linear relation on the set, on the linearly independent set. U1, U2 up to Uj. And which is a contradiction. Because for any linearly independent set, we don't have a non-trivial linear relation. We don't. Right? Because the difference here, they are all different. They are all non-zero. And one of alpha 1, alpha 2 are non-zero. So at least the one coefficient is non-zero. That's why we call this relation is non-trivial. Okay? This is non-trivial. Because in here, the alpha j's are not all zero. So some alpha j, alpha I is non-zero. Right? A contradiction. All right. So the assumption, is wrong. Okay? So we conclude that U1, U2 up to UK is linearly independent. Okay, so we have done. Right, so I stop here. Sorry for my extended lecture today. I haven't finished yet chapter 6 a little bit in left. So I will continue the exposure next Wednesday. No, we don't have. So I will. So the midterm examination will be tethered to update to my exposure to chapter 6. But why I will ask you to read the textbook, right? The whole chapters. I think you will now have the ability to read through the textbook. Okay. All right. So that is for today.